Hello, in this video we're going to be looking at Format 3 from the Protostar exercises. So it's been a while since we've looked at these, but Format 3 is actually the fourth format challenge in the Protostar series, which by the way has migrated to this new domain. So if you want to follow along, you can download the image, or if you have the previous image, it's the exact same. But in this video, I'm also going to be showing you how to set up the disk and also port forwarding so that you can run it from your own machine. Okay, so we're of course going to be doing this running the VM in VirtualBox. So the login is just user for the login and user also for the password. So to set up port forwarding, what you have to do is look at the IP address information for this VM, and you can see here on the second slot we have the IP 10.0.2.15. And if you try to connect to this, if you try to SSH to this via your own machine, you will actually see that it does not work, mainly because this doesn't actually have the adapter to actually connect. So to solve this issue, you can go to Devices, Network, and Network Settings. And from here, you go to Advanced and select Port Forwarding. So these are the port forwarding rules that you have for the VM. And I've already added this rule here, but initially you will see that there are no rules. You can just add one here and specify the guest IP, which is the address that you see here, as well as the port, in this case 22 for SSH. And you can forward that to the host IP and the host port, and you can select these to be anything you want, but in my case I have just chosen 127.0.0.1 port 2222. And once you get that set up, you can go ahead and open up your own terminal and SSH to user at the address, and make sure to specify your port as well. And if this is not your first time to do this, if you restarted the machine, then you will get some message like this, where basically you have the remote host ID has been changed. So this is just to protect you from man-in-the-middle attack. But of course we know that this is just running here, and there's nothing that we have to worry about. So we can just remove it with the message that it gives, and then rerun. And of course we get the message to continue connecting. Just select yes, log in with user as the password, start the bash shell, and here we are. So the directory is in opt protostar bin, and here we see all the challenges, and today we're just going to be looking at Format 3. So I've done one video, pretty short video on a format bug before, but we haven't actually looked at actually modifying memory and changing program execution in that way. So in this video, I want to actually do that. And I believe Format 4 is actually modifying the program execution, but we will look at that at a later date. So here's the source code for Format 3. We can see it's pretty straightforward. There is a global variable target here, and 3 functions. Main just calls vuln here, and vuln sets up the buffer of size 512, and then we do an fgets into this buffer from standard in, and then we call print buffer on the buffer. And print buffer is defined here, and all it does is just calls printf on the string that we pass it. In this case, it's just the buffer. So essentially, we have complete control over this format string. We can put in any format string printf specifiers, and we can get some unintended execution. So we can just test that out real quick here. As we did in the previous video, all you have to do is just run this, and it's waiting for input, so we can just give it something like %08x, and we can see that we get something like this. And of course, this is not the correct behavior because it is treating our format string as an actual control format string. So it will actually read this value from the stack. So the goal, of course, is to modify target to this random value here. And if we do so, we get this message. Otherwise, it will actually show us what target contains at the end. So this will be very useful for helping develop the exploit. Okay, so to get a better look at the internals of this program, we can actually SCP this binary into our local directory and run IDA on it. So I'm just going to go ahead and start IDA. Here we go. Just select go, and we'll select open here. And we can open the challenge from here. So in this case, it is Format3. So here's the binary. And then we can see what's going on. So here is the main function. And this is pretty much what we expected. It just calls vuln. Vuln gets, let's see, gets 200 hex. So that's the 512 that we're looking at. It reads that from standard in, you can see here. And it reads that into the buffer. So the buffer, if we look at what we have here, is at EBP plus S, and S is located at negative 208. So it's EBP minus 208. Now that really doesn't matter for us right now because we're not doing a stack exploit, so we don't really care where this offset is. I guess the one thing that we do want to keep in mind is just to make sure our input is less than this 512, and that of course shouldn't be a problem. So after this fgets, we call print buffer, and print buffer we saw is just called a printf on the first argument that we passed to it. In this case, it is at EBP plus 8. Okay, cool. So, and then after that we check the target. So the first thing we want to find out is the address of target, and we can do that simply by clicking on this and looking at the address here. And we should make a note of that. So target equals hex 080496F4. So this is the address that we want to modify. Okay. And the exact value that we want to modify it to is 01025544. And I'm just formatting this to make sure that we can see that exactly what we want to do. So actually, to construct such a format string that will modify this memory, there are a couple of ways to do that, but probably one that is optimal. And the best resource to just read about this is this paper by the, I think it's a Stanford, some lab at Stanford, and you can see that just the fundamentals of the format string exploit, as well as ways to construct format strings, and this particularly overriding of arbitrary memory is what we want to do. So the main format string vulnerability for writes is this specifier called %in, and essentially what it does is it writes the number of characters that have been printed to the string. I don't know if I can even find it at this point. It writes it into a address in memory. So the weird thing about it though is that it writes it as an integer. In other words, it writes 4 bytes, but the counter loops around every 256 characters. Here it is. It loops around. So in other words, when we get to 255, it will reset back to 0 when the next character has been written. So that means that we can't just write like that huge number of bytes into this reference. We can't do that because it will reset, and the best we can do is just get this 44. But the trick is, of course, that you can write it sequentially and you can write it so that you don't overwrite the previous one. So you start at 44 because it's a little Indian, right? So you start at 44, you write the 4, so you get 0, 0, 0, 44. And then you write to the target plus 1. So instead of F4, you get F5, and you write this 55, and you'll get zeros padded down. And then you so on until you get to the end here. So the last address you'll write to is 080496F7. There are some problems with this, of course, and it's that you have to perform a lot of writes. In this case, you have to perform 4 writes, right? So that's not desirable. And another thing, and it discusses in this paper, is that you will overwrite things that come after this reference in memory. So if we look at what we have here, there's actually some stuff that is after, and I don't know if overwriting that will actually affect anything or whether that'll be a problem at all. But in general, it's not desirable to do that. However, there is a workaround for this, and that is to use a %hn specifier. And what this does is called a short write. And this is actually better because what it allows you to do first is you can write 2 bytes at a time. So the H stands for short. So a short is 16 bits or 2 bytes. So you can write anything from 0 all the way to 65, 35 into a reference. And the other thing is it also does not destroy data beside the address. In other words, it writes exactly 2 bytes. It writes up to and exactly 2 bytes. So in terms of our exploit, what that does is we can write 5544 in one write and then 0102 in another write. And we don't have to worry about messing up other memory. So the first write will be to this F4 and then the next one to F6. Okay, so how do we actually get this working on this particular binary? So if we go here, and let's just go ahead and see where in the stack relative to our format string parameter is our actual string. So let's go ahead and do this. Okay, so to find that out, we can just do a lot of these %08x and see if we get something interesting here. So if we look, there is a lot here, and if we look at the result, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then is that 12? I'm not actually sure if that was 12. We can actually count that. Oops. So let's go ahead and count how many characters there are in here. Just do something like this. So that was 88. So actually that was 11. So that was 11 double words. And then we get something interesting, 78, 38, 30, 25. Now keep in mind this is still presented in big Indian when we printf. So to actually find what the memory is, we read backwards. So it's 25 first, then 30, then 38, then 78. So 25, of course, is this %, 30 is 0, 38 is 8, and 78 is the lowercase x. And we can see this pattern repeats over and over and over again. So this tells us that our actual format string text begins at 12 double words beyond the parameter. And a neat thing about format strings is that you can actually specify which word you want to use. So we can say %12 $08x, and we can see that it printed 24, 32, 31, 25. And if we read this backwards, it's %1, 2, and then this 24 is actually the $. So now that we have a reference to our string, we can go ahead and put our address actually on the stack and then reference that. So to do that, let's go ahead and construct the format string. So the address that we first want to write to is 080496F4. Right, so those will have to be the first bytes in the format string that we send. So when I do this \x here, that just means the C kind of style, which means that this is a byte. And of course, actually all of these are printable, none of them are null, which is really nice. So this is the first address we want to write to, and then the second address we want to write to is F6960408. So now we have these two addresses. So the first thing that we want to do is get the internal counter to 5544 hex. So that at first seems kind of challenging because that means we have to type in literally, in our format string, we have to send in that many characters. But of course our buffer isn't even that large, and even if it were able to do that, it would likely not succeed because of some limits in terms of the standard in and buffering and all that. And plus it's just not a neat solution. So instead, what we can do is utilize a property of the format string that allows us to specify the width of the print. So as you can see in the format string that I passed in earlier, we used the 08%08x. And what this is basically make the width of the printed value 8. And then the 0 is just basically padding if it's not 8 bytes, it would just pad with zeros. So we can do something similar here. Instead of 8, we can do a huge number that we can specify. So what we can do is just go to our calculator, and the first value we want is 5544. Right? But actually this is not what we want, because we've already printed out some stuff here. So if we do 5544, it will just add an additional 8 to this, which will give us 55 for C, which is not what we want. It will give us a different value. So to address that, we just have to subtract 8 from this. We can see we get 55.3C, and the decimal value is 21,820. So this is the number of characters that we want to write in our next step so that we can get the internal counter to 5544. So to display just any random value, we can just do %21820D. So what this will do is take that first value from the stack after our format string pointer, and it will print out that as a decimal in a field of 21,820. So as you can imagine, it'll just be a bunch of spaces or empty things, and then at the end will be the decimal. And as we've seen before, the first value after our format string pointer is 0. So what we should expect is a 0 there, padded with a bunch of these spaces. So after this, our counter is correct, and we want to go ahead and write the value of the counter into a location in memory, and this location in memory is exactly here. So first we have to reference that value. So remember, it's the 12th word on the stack. And then the actual value we want to do is hn, just as we saw in this paper. You do a %hn specifier to write a short. So the next thing that we want to do is update the counter to now have 0102. But you may notice 0102 is definitely less than 5544, right? But again, as I mentioned before, after the count reaches a certain value, it loops around. And in the case of short writes, it's 2 to the 16. So to find the number of characters we write next, we can just add a 2 to the 16 to that. So in that case, 10102, So we're just taking this, but we're just adding an additional 1. And then from here we can subtract 55.4 to get A, B, B, E, and this is the number of characters we want to write next. And this is 43,966. So again, 43,966 D. So this will display the second argument beyond the pointer to our format string. And it will do that, it'll pad it with 43,966 empty spaces. And this will update the counter to our desired value of 0102. And then we can go ahead and write that to the 13th value. So in this case, the 13th value or address reference here is F6, which is exactly what we designed it to be. And then we do a short write like this. So this is going to be our format string. So all we have to do is just bring that in here, do Python C, and then print, and we'll just print this binary string, and we'll pipe that into Format3. So if you run this, you'll see that it doesn't work for some reason. The target is 0000, so that is strange. But the reason why it doesn't work is because actually these $signs here, and when you run this in bash, you actually have to escape it because it will replace the $sign with the path. So when you run this, you will see that you have modified the target. So I hope you guys enjoyed. This was the first format string exploit where we did an arbitrary write to a location in memory. And essentially the attack strategy was to find the address of target. You can use IDA or GDB, it's all fine. And then the value that we want to write to it, and then construct a payload that will first of all reference itself, as you can see with the 12 and the 13 here, the 12th and 13th words, which are exactly pointing to this one and this one, respectively. And then updating the internal counter via these huge buffered writes here to get the desired value in the internal printf counter, and that will give us the correct writes, the correct values to write into the target addresses. So I hope you enjoyed, and in the next video we will use this exploit to obtain arbitrary execution.